videos that go along with your lecture slides that are posted on Canvas. Find comfort that section 2, which is portions 4 and 5, sections 4 and 5 from this chapter. This video will be significantly shorter than our previous video. A lot of this material is kind of just prepping us for our third section and really comes back to a lot of review of 152 material. Please email me if you have specific questions, but I'm going to kind of jump around in this lecture section to just kind of highlight some important parts. It is crucial that you do go and read these sections as well as read through these slides and ask any questions that you have. So the first thing that you're going to need to be able to do to move forward successfully with this section is to remember your electronic configurations. So remember, when we're doing electronic configurations, this is the things where you have 1s2, 2s2, 2p6, 3s2, so on and so forth. This is a way that we organize the electrons in an atom or an ion. We can do it for an ion as well, whether it's a cation or an anion. And it's really important for when we're identifying the number of valence shell electrons in an atom or an ion and where they're located. So, couple of things just to bring up, right? When we're doing electronic configurations, and we're talking about stable compounds, so stable situations where we don't have anything crazy going on, we want to remember things like two nonmetals, right? They are going to form covalent bonds. And when they form these covalent bonds, both of the nonmetals are obtaining noble gas electron configurations, which means they would have 8 valence shell electrons, right, between the shared atoms. When a nonmetal and a representative group metal react, so again, now we're talking about something like a potassium or a sodium or something like that, we get what we call binary ionic compound. Binary standing for 2, metal, nonmetal. Ionic compound because it's a give and take of electrons. So remember, again, everyone's trying to get to a noble gas configuration, but unlike in a covalent compound where they're sharing the electrons to achieve that noble gas configuration, in an ionic bond, the metal is giving up electrons to attain a noble gas configuration, and the nonmetal, the anion, is going to be gaining electrons to achieve that noble gas configuration. So we need to start thinking of our ionic compounds in terms of like their crystal lattice, so their solid form. This is just like if you had a cube of cations and anions, right? This is just one face of it. And we're just kind of showing you that there are a lot of positive and negative ions that are packed together in these solid ionic compounds. And just like we talked about earlier in Coulomb's law, we have positive attractive forces, right? A negative and a positive, they're going to have attractive forces. And we also have repulsive forces. In this case, an anion that's close to another anion would be a repulsive charge. This image doesn't also have it here, but there would be a repulsive charge between these two cations as well. Obviously, when we're in a gas phase, if we're dealing with non-ideal gases, right, we're moving on from our ideal gas days where we said it didn't matter what they were. We know that if we had gas phase ions, that some of the same attractive and repulsive forces would be there as well. So we use electronic configurations as a way to predict the formulas of ionic compounds, right? So go back to 152. If I tell you we have iron 2 oxide, that has a different formula than iron 3 oxide. And how do you figure that out? You should be comfortable doing that. If you do need some resources, please email me and I will give you some resources for that. Now, we know that a calcium will give up 2 electrons and become a calcium cation with a +2 charge. We know that the oxygen wants to take on those 2 electrons and become an oxygen with a -2 charge. So we know that a cation with a +2 charge and an anion with a -2 charge, those will be electrostatically attracted to each other in a 1-to-1 ratio. This is kind of just a cheat sheet, if you want to call it that, if you haven't remembered from back in your 152 days about the different kinds of cations and anions that form in terms of the periodic table. Again, this is kind of saying these things in word form that go with this figure, but that group A metals will lose 1 electron, group 2A metals will lose 2 electrons, group 3A metals will lose 3 electrons, right? Non-metals in group 7A will gain 1, right? And in group 6A they'll gain 2. There are some oddballs, and for your homework you will need to know these exceptions to the noble gas configurations. These are primarily with our transition metals, so we know transition metals, like 90% of the time we just look at our anion, and that helps us dictate what the cation charge would be, right? For our transition metals, this is how we figure out whether we have iron 2 or iron 3, so on and so forth. But we do have some of our transition metals where they only form certain configurations, and this has more to do with how many electrons are in that d orbital and kind of different things they will do to kind of lower energies. This is why tin will only exist as +2 or +4, the same with lead. Bismuth and thallium, or bismuth will have a +3 or a +5, and thallium will be a +1 or a +3. Again, you really need to know these more for your homework. I won't necessarily be asking specific questions on test or quizzes with these. The first new thing we're going to talk about is ion size. This is very, very similar to what we did when we had atom size, but now we're talking about the ions. So if we're talking about a cation, we're talking about the size of the atom after it's lost 1, 2, 3 electrons, and if we're talking about an anion, we're talking about the size of the atom after it's gained 1, 2, 3 electrons, right? It's very important because this helps us understand kind of the stability of that ionic solid, of that crystal lattice, that solid form that the ionic compound takes on. It also helps us predict things like if it will be aqueous in solution, i.e. will it be soluble. And then we also have some biological effects with that. It helps us predict what it might do in, for example, our bodies. So there are two main factors that are going to affect the ionic size. The relative size of the ion and what we call its parent atom. So we're talking about an ion and the parent atom. This would be sodium, the atom, and sodium, the cation. Na, Na+. That's what we're referring to. So obviously, if we're comparing something like sodium and cesium, we know that the periodic trend for atomic radii increases as we go down the table. The ionic radii would fall in that same category. So again, a positive ion is formed by removing 1 or more electrons from a neutral atom. So the resulting cation is always going to be smaller than the parent atom. So again, the parent atom, if that is a sodium atom, the sodium cation will be smaller, and this should make sense. Write out your electronic configurations for a parent atom and its resulting cation, and you will see that you've gone down an N shell, right? Because when we lose those valence shell electrons, we're going back to a noble gas configuration that came before it. So if you're at N equals, if you're at 4s2, the cation for that would be 3p6. So we got rid of that N equals 4 shell. So it got smaller. Negative ions, conversely, are going to be adding electrons. So they'll be bigger than their parent cation. And then we need to talk about their position in the periodic table, right? Just like I said earlier, the atomic size increases as we go down the periodic table. We will see the same thing happen in ionic sizes. In a given period, right, we're going to give up electrons to form cations, and we're going to accept electrons to form anions. So we can use that as a way to kind of help guide us. One thing we can talk about is the isoelectronic ions. This is a series of ions that all contain the same number of electrons. An example of this would be O2-, F-, Na+, Mg2+, and Al3+. If you look at all of these on the periodic table, they all have the same electronic configuration. Okay? And the trend is, right, the size decreases as Z, which is a fancy word for the nuclear charge, increasing. This is a general table to, or I guess image to show you the ionic trends in radii. So lithium to sodium to potassium to rubidium. Just like atomic radii, as we go from top to bottom, we get larger. And again, what will be weird here is we have to remember if we're dealing with something that is a cation or something that is an anion. So as we go in our cations from left to right, we will get smaller. And as we go from our anions from left to right, we will get smaller. But our anions will be bigger than our cations in the same period because the anions are gaining electrons and the cations are losing electrons. This is our door question number 2. Again, like we had in our previous video, these are important and will be treated just like we treat door questions when we were having classes on campus. So I'll leave this up here. It would be good for you to practice, get some ideas on how you would answer this question. It might show up on tests and quizzes. All right, this would be a good question for you to pause on. Go ahead and arrange the following atoms in order of decreasing, atomic size or ionic size. So to do this, we have to first look at each of the atoms present. Since all these ions have the same number of electrons, aka this is an isoelectronic series, right? They all have the same electronic configuration as krypton. We can look at their size depending on their nuclear charge, or what we call their Z value, right? For Se2, it's 34. For bromine with a -1 charge, it's 35. Rubidium would be plus is 37, and strontium with a +2 would be 38. So we would have our cesium as our largest and our strontium as our smallest, and we'd go in that order. Which of the following has the largest radius? Again, these are things that you would actually need a periodic table in front of you to do, so pause for a second, look at your periodic table and come up with your best answer. In this case, the largest radius is determined by its charge, right? So again, if we have an option of a 2 charge, a 1 charge, no charge, a 1 charge, and a 2 charge, 2 charges are the greatest. However, we know that a cation means that we're losing 2 electrons, so that's going to get smaller. Where an anion, this means we're gaining 2 electrons, so this would be the one that is going to be the larger of the radii. We need to talk a little bit about lattice energy. So we talked earlier about the idea that these crystal lattices, these solid ionic compounds, that the way they kind of form their solid helps determine things like its solubility, its readiness to do so. There are some biological aspects to it. So we need to talk about the energy that is kind of held in the bonds of these solid ionic compounds. The change in energy that takes place, the way we usually measure this is going from the gaseous of the cation and the anion to the solid of the ionic compound. And this typically is done on like a 1 mole scale. So what is the energy it takes to turn the gases of the reactants into 1 mole of products? That's what we're usually considering when we say a lattice energy. So it's defined as the energy released as an ionic solid forms, right? So this is high energy. These are gases, right? So there's a lot of energy in those. And as they form the solid, energy is released as that happens. Because it's energy released, think back to our thermochemistry days, right? This means that lattice energy should have a negative sign. So for example, in the formation of lithium fluoride, we have lithium, the solid, plus fluorine gas gives us lithium fluoride, right? This is a balanced chemical equation. Now, there's a solid over here. We know that when we're doing lattice energies, this needs to be a gas. So the first thing we're going to have to do is take our solid and turn it into a gas. And you wouldn't need to know this off the top of your head. I'm just going to tell you that the enthalpy to do that is 161 kilojoules per mole. Then we need to go from lithium gas to lithium the cation, and there's an energy associated with that as well. These would be all energies that would be provided to you, or you would be solving for one of them with more information. In this case, we're telling you it's 520 kilojoules per mole. And then lastly, we would need, or not lastly, but we also need to figure out the dissociation of the fluorine molecules, right? We know that fluorine is diatomic, so it exists as F2, but we don't want F2, we want F. So we would have to have an energy associated with taking 1/2 of F2 to get F. And we're telling you that to break this bond, it's 154 kilojoules per mole, but since we're only taking half of it, for what we would need would be 77 kilojoules per mole. And then lastly, we need to make our the energy associated with turning fluorine gas into fluorine the anion, which we have at negative 328 kilojoules per mole. So when we put all these together, the formation of lithium solid from the gas cation of lithium and the gas anion of fluorine is negative 1,400, or excuse me, negative 1,047 kilojoules per mole. Now, when we put all this together, it looks something like this. So this may be similar to what we talked about when we did like Hess's law and things like that in our thermochemistry. But each of these processes, right, we had this overall reaction. We said this was our overall reaction. How are we going to get there? Well, if we're at lithium solid, we know we need to go into a gas. There's an energy associated with that. And we know that lithium gas, once it's that, needs to become a cation so that we can make this ionic compound. So there's an energy associated with that. Our fluorine gas needs to be just, our F2, right, needs to go to an F that's already a gas. And we only need half of it, and there was an energy associated with that. We know that F now needs to become an anion. There's an energy associated with that. And then there's an energy associated with the cation and the anion coming together through electrostatic attraction. There's an energy associated with that. So this process here, right, when we sum all these up, gives us this overall energy. And it's, like we said, per 1 mole of whatever ionic solid we're talking about. We can look at this in terms of an energy diagram. You should be comfortable with drawing an overall energy diagram. It won't be something where you have to know necessarily the energies associated with it, just in general terms that, you know, the process of taking lithium cation plus fluorine the gas going to fluorine the anion, that this is a negative here, and that these two added together is another negative here, and that to go through all these processes are all positive, right? So these are all endothermic processes, these are all exothermic processes, and that we have an overall change, right? This is why we have a negative, this is why energy is released when we go from the gaseous state, right, the started state here of these materials to our solid state here. We see an overall change. So this is why energy is released, why it's an exothermic process. Now, often we talked about this a little bit, the energy calculations, right? We're kind of going back to like a Coulomb's law here. Again, for purposes of what we'll be doing, your homework, you'll have a couple of examples of this, but we won't be going into too much detail with it. But basically, when we have this lattice energy, right, the amount of energy it takes to form 1 mole of a solid ionic compound, we take into account things like the size, right, the shortest distance between the centers, the cations and the anions. So this is the radii between those two atoms. So the size of the two ions, not the two atoms. The size of the two ions, as well as their charges. These are the two factors that affect lattice energy. So lattice energy will have a negative sign, right? It'll be exothermic when the charges have opposite signs. This makes sense. This would be my cation, this would be my anion, a positive charge and a negative charge. That's what wants to form an ionic compound. So it will have a negative sign, so it would be exothermic. Processes become more exothermic as the ion charges increase and the distance between the ions in the solid decrease. So the smaller the ions are and the higher the charge they have, the greater the difference in exothermic energy will be. So, this is a good example for this. Which of the following ionic compounds has the largest lattice energy, aka the lattice energy with the most favorable stable lattice? So the one that is going to have the greatest exothermic value, the most negative value. So to do this, you're going to have to go through and compare each of these compounds for their size and their charge. So take a minute and determine for yourself which one you think this would be. So lattice energy is directly proportional to charge and size. When we look at these, we see that we have MgO, +2, -2, right? This is -1, -1, -1, +1, right? -1, +1. So all of these are lower in charge. These are higher in charge. There are examples in your homework where you will see it be equal charges and different ionic sizes. So you'll have examples of both. That is the end for this section. If you have questions or you need a review on electronic configuration, please let me know.